I see there is a bit of evaporation in the room, little by little. But you know, when we can call it distillation, so then we keep the best. little by little. Some people disappear, but probably the best is remaining, so that's cool. Brief recap. We have seen quite many things around soft matter. I like to put this context in this idea of living properties. Living systems are part of soft matter. We are made of soft matter. Process work also at KT. And there is this diversity and unity in soft matter, which is something I found extremely interesting. And we have all these properties. We want to approach this kind of dynamic properties and using always synthetic systems because we can control it. And this is a way we can understand how we can make. And there is these two-side objectives to get this knowledge so we can understand better, and this can be useful to have synthetic system because we can control them. And at the same time, if we can make objects, this is something also interesting, so that we can get interesting materials. But there is something that's actually I have not talked so much so far, and I think in general we didn't address that much, is actuation. I mentioned a lot of programmability, using DNA, for instance, a lot of also reconfigurability that we could see, especially yesterday. I showed you that we can have nanostructure that transform. We can have also, in the synthetic biology approach, we can make objects that move, that have this kind of interesting behavior. But we didn't see much about actuation. And so today, this talk will be mainly about actuation. Okay? So now I will go to the more detailed talk. And we'll be able to go a little bit inside this. So today, I would like to speak about soft matter actuation. It's something I have been interested for many years. It's actually somehow when I started as a researcher, as a permanent researcher, I was interested in this idea of actuation. You tell something to soft matter and soft matter respond, you know, so this is quite interesting. You can talk, you do something and you have a response. And what is nice with soft matter is that because you have something that is organized around KT, it's organized, but it's easy to be disorganized, and then you can communicate with soft matter. You have this idea to have, you can do actuation, you can do something, and you have a response. So today I will mention mainly about two types of actuation, light and magnets. Lights because I don't know, there is kind of, I think most of people on Earth, they like light. It's like something that we feel, I don't know, comfortable and maybe the symbol of knowledge. But it's also an interesting stimulus for different aspects. First, it can travel distance, so you have this idea that you can have remote control, something quite interesting with light. This is one thing, this remote character. The second thing with light is that it's something you can tune. Light, you have a lot of information in light. You have the wavelengths, you have the power, you have the optics you can do, so you have information you can put in light. And the third thing is you can achieve quite good spatiotemporal resolution. We are limited by the diffraction limits in general with light actuation. Diffraction limit, we are, let's say, half micrometer. So we can still do things that are quite interesting down to the micro scale with light in terms of spatial resolution, and there is excellent temporal resolution. So we can have good spatial temporal resolution with light, and if we see the screen, you see that with light we can do some quite elaborate pattern. Yeah, this is just light. This is a display, but I could use a projector and I could make the same image. So you see that with light I can send a lot of information. So it's an interesting stimulus for these aspects. And I really like to see how objects respond to light, because there is something a little bit, magic inside. You will see, if you check papers or if you look in literature, you will see a lot of research done with photoresponsive systems. At the same time, I always think it's important that we keep thinking like, in reality, in our real world, are we using light to control things? Not so much. Not so much. There is not so many examples in the real world that we are using actually light to do things, especially to control things. There are a few examples, but there are not so many. Like you have glasses that will use some photochromes so that their absorbance will change depending on the wavelength. So when there is UV, it will become less optically transparent to protect the eyes. You have these kind of things, but there are not so many. And the reason for that is that we are not transparent, right? I have difficulty to see the person which is behind you. Yes, you are not transparent, right? And it's something you need to keep in mind. We are not transparent. So devices are not transparent in general. Okay, maybe you can have an aquarium, but most of the things we have are not transparent. So just to keep in mind. And, you will see also many people speaking about spatial temporal control, and you can cure people because you have spatial temporal control. So I will target a tumor and so on. Yeah, go for it. Put light on your patient. Light is not going in so much inside, right? So just keep in mind that, okay, we'll show things, cool things with light. It's a spatial temporal resolution. It's remote. It's beautiful. It's kind of magic. So it's very interesting to work with light. Just keep in mind that life is not transparent. So we have just to keep this as a background. And I will not show many things, but to me, magnets are very cool. So it may be less fancy, than light, because you feel, okay, magnet is for children, I don't know. But what is nice with magnet is that you can use magnet in the real world. And there are so many devices that work with magnet. So many. My plug here is magnetized. It's a magnet that connects my computer. It's not like some strange light control or whatever. So there is a lot of devices working with magnet because you don't have this problem of transparency. Everything is transparent for magnet. This is something very interesting. So I will just show just one example with magnets, but I think it's an interesting stimulus. Okay, so I put this in the context of microfluidics. And so if we want to combine light and microfluidics, we reach a field that is called optofluidics. And optofluidics is a way where you combine light and fluidics. And in general, this world of optofluidics was the opposite. It was to use fluidics to do optics. So this is how the field of optofluidic emerged. There was people who say, let's, instead of controlling light with solid state material like lenses, I will control light using liquids. So for example, I have a channel and I have a liquid And I will use this liquid as an optical guide. And I will use liquid, for example, to make a laser. Instead of pumping my laser in a cavity, I will do it in a liquid. So at the beginning, optofluidics was the idea of using fluidics to do light. And me, I wanted to do the opposite, try to use light to do fluidics, and that's why I call it, at that time it didn't exist so much, I call it light-driven microfluidics. So, what is fluidics? In the study of fluid and flows, so it's a science, but it's also to control fluid, and it's also a technology. Okay, so microfluidics is both a science and a technology. And it's microfluidics, so you deal typically with size that are below the size of hair diameter. So typically micrometer. So how microfluidics is working, there are two ways. Either you flow liquids in something, so through microchannels. These microchannels exist in nature. We have blood capillaries, we have lymph veins. You have also microfluidics you can build in your lab, and you can even buy in a shop. There are many already existing microfluidic devices where you have a small amount of liquid that is controlled. This is an example of a pregnancy test, for example, where you just put a piece of liquid and you can do something inside. And of course, there is this idea that if you integrate many operations, you can build a laboratory on a chip. This is famous picture in the lab from George Whiteside's, and you see that you have you can think of integrating a lot of operation, a lot of things on a very small size. It can be chemical reaction, analysis, it can be separation, it can be a lot of things that you try to squeeze a whole lab in a very small piece. It's like microelectronics, but for fluids, okay? So what you should remember about microfluidics, something you should remember is that currently we are in a stage that there is no big challenge in fabrication. So you can fabricate practically anything you want as soon as you are above a micrometer. It's a bit more challenging where you reach 100 nanometers. There are methods, but I would say from 1 micrometer to millimeter scale, there are methods. So either you can do, I can do, either you cannot do, you ask a colleague, or you buy. So there is no challenge in microfabrication. You can do any channel shape and size you want, basically, and you can practically a lot of types of materials. It can be PDMS, like silicone elastomer, of course, but you can also use epoxy, plastic, glasses, and so on and so on. There is no scientific challenge in the fabrication. The challenge is in the manipulation of liquids. And another way to do microfluidics is to do it without containers. So your elemental piece of fluid is not confined by physical walls, but it's free. And then what can we do is just use interfaces, as we all love interfaces here, and you can just do droplets. Droplets, we know them very well, they exist in nature, and you can manage to build droplets. Okay, so to build droplets is not so difficult. So you have mainly two ways to do droplets. In one way, you just put a liquid in another liquid, okay? And here you have a competition between surface tension and viscous forces. So if your flow is very high, your system is controlled by viscous forces, so you will stretch the interface and you have a jet. So this is a regime of high capillary number. But if you are at a low speed, then surface tension will dominate and the liquid will try to avoid this interface stretching, so it will make droplets. So this is low capillary number. So we could think that, okay, like we have Reynolds number to know if it's a laminar or non-laminar regime, we could just compute the capillary number to know if we are in a jet regime or in a droplet regime. You can compute that. The problem is that in microfluidics in general, you are in a channel. So you have a fluid, for example, water, another fluid, oil, but you have also your channel walls. And in this case, you cannot just consider the capillary number, which is just between at the liquid-liquid interface. So you have to remember that when you do microfluidic with droplets, you have something very important. You have another interface that is very important, is a solid-liquid interface. It's the interface between the channel walls and your continuous phase. And this is mainly controlled by wetting. So when you do microfluidics and you want to do droplets, you don't care so much about capillary number, you care a lot about the wettability. So usually you will do, if you want to do droplets, you will use channel walls that are in non-wetting situation for your dispersed phase so that it will form droplets. This is just a small thing. So you can have micro droplets in the lab, and you can generate with a microfluidic device, and you can manipulate these droplets on surface using wetting. This is electrowetting. So I will just mention a few things. You create a gradient using changing locally the wetting so you can transport droplet. Okay. So, as I said, if you have this tool, and if you integrate many things, you have something called a lab on a chip, and you can do basically any operation you want or you can imagine for. Very simple consideration about microfluidics. For me, there are three characteristics. The first is you deal with very small volume. Your scale has a size to the power 3. So 100 micrometer is already 1 nanoliter. So you take a pipette, micropipettes. You can, if you are very careful scientist, maybe experimentalist, maybe you can manage 0.5 microliter. But maybe you see during the hands-on experiment that it's not so easy even to manage 10 microliter. So you have to imagine that here we are already 1,000 times smaller than the smaller volumes you can do with a micropipette, and this decreases dramatically. So each time you decrease by 1 order in your size, you decrease by 3 orders of magnitude in volume. So in microfluidics, we be very easily in the picoliter regime, extremely small amount of volume. So what are the consequences? What could be interesting to have small volumes? What do you think could be? What can be the interest of having small volumes in general? You are all tired by the DNA challenge or what? Okay, nothing very complicated. So, first, you have very small volume. So you can do, instead of working with one piece of stuff, you can parallelize. You can have many small volume. Parallelization can be interesting. For example, ice cream. You know that in chemical engineering, people develop a reactor that is very nice, very nice, that optimizes the energy, the transfer, and so on. So it's very efficient. And then people want to scale up, and when they scale up, nothing is working anymore, and all your great optimization you have done is lost. And this is a big problem for the optimization, but also for the safety. You know, for example, in polymer, when people are making polymer, sometimes you have a reactor, and suddenly everything polymerized in the reactor. So imagine how it can be dangerous to have like huge tower where everything suddenly becomes solid, where you deal with temperature and so on. So it's problematic. So there is something quite interesting conceptually. So instead of doing scaling up, you can also parallelize. So if you have a very nicely optimized reactor that optimizes the transfer and everything, that is very good, for example, to optimize energy, then instead of scaling up, you can parallelize. And there are actually companies doing that, especially Ben & Jerry ice cream, it's American ice cream, they have this optimized microcassette reactors to make some foams and so on. And instead of trying to make big things, they parallelize. So you can parallelize, so this is one way, like you can replicate something, but you can also do high throughput screen. So you can screen many compositions, many conditions, and then maybe we'll find something very interesting. Another thing that is very naive, but it's quite interesting, is the sensitivity. So I made a very simple drawing, but imagine you have one pathogen in a swimming pool, okay? Or imagine that, you know, when you have a cancer, for example, in your blood, you can have circulating tumor cells, but they are a very, very small number compared to the millions of cells you have in your blood. So you have to deal sometimes with concentrations that are small, not because the number are small, but because the volume is large. And if we think, if you look at nature, and biology works, actually biology works not at a uniform scale, but at the local scale. And that's how cells can communicate and understand each other, is because they are able to deal with concentration and not with number of molecules. So how you deal with reasonable concentration when you have a small number of molecules, you just decrease the volume. So if you have compartmentalization like that, here I have zero concentration, but here I have a high concentration. And if I am sensitive to concentration, like many things, like when you measure a pH, you are sensitive to concentration, not to number of molecules. You see that if, for example, this is a proton, if I put my pH here, I can measure the pH, no? And here I cannot detect it. And this is how living cells are working. They emit a small number of molecules because they cannot produce so many molecules, but locally the concentration is very high. So if now, for example, I have my cell in a microchannel, then I will be able to, by measuring reasonable concentration, I will be able to detect very small amount of molecules. So there is this very interesting idea that if you go to small volumes, it's very simple. It's just concentration equals number divided by volume. But because you can really go to very small volumes, you can deal with high concentration. So on one side, you can increase sensitivity. On the other side, you can also manipulate very small amount of molecules. So you can go to single molecule manipulation, for instance. And the third aspect, that is also very interesting, is that you can go to single molecule or single cell analysis. Why is it interesting is, imagine you have a water pipe and you want to give this water to a population to drink this water. And I heard there is some strange amoeba in Kerala, but it could be amoeba, it could be a bacteria, a pathogen, it can be something. That the problem is the problem is not that this something is in for instance, low concentration. The problem is that something is mixed with many other things. Okay, for instance, bacteria. You have a lot of bacteria in the natural world, and they are necessary. We have, as you know, we have more bacteria in ourselves than cells. Okay, so bacteria are important. We should not remove bacteria, for example. But in bacteria, maybe among millions of bacteria, you have one that is very dangerous. The question is, how can I do? If you do this, if you compartmentalize, you can analyze each system, and maybe among this guy, you will have a very important phenotype. For example, a very dangerous pathogen. So this idea is called digitalization. So this idea is to do digital microfluidics. It's quite interesting. Like you can really go to single objects, single cell, and then you can do the analysis. And then if you use the power of molecular biology, you have a cell, then you can do PCR, you can amplify. So if you combine this idea of single objects with amplification, then you can start to detect things that cannot be possible if you just do a bulk measurement. So this is just examples of the big, some kind of directions that are interesting in microfluidics. So microfluidics, I see it as a tool. Okay, there are some scientific aspects behind, but it's mainly a tool. There is not so many science to do it, but it's an interesting tool. And as I take this brush with the same tool, you can do different things. I am vegetarian, I will never do this kind of things, but you can, do different things with the same object. And you see going from chicken brushing to Matisse painting, there is a big world. And it means that it really depends what you do with this tool, okay? There is nothing especially great in microfluidics, but then you can use it and maybe you can do something interesting. So there are so many things you can do with microfluidics in chemistry, in biology, in medicine, in analytical science, in physics, and so on. I think in medicine, there are really the main three main things is this idea of, doing the diagnostic directly at the patient rather than to ask a patient going to hospital. This is very promising for developing countries where hospitals exist, but usually they are far from people. So hospitals exist, but they are very far. And for some people, it's very difficult to go to hospital. So they can go, they can say, okay, I will go to hospital, but they really need to have a reason. And then if you are able to do your diagnosis directly at the people, place, and time, then maybe you can really dramatically change things. So it's very important part, this point of care diagnostics. And then with this idea to bring diagnostics to people, there is this idea to make diagnostics that are accessible, that are inexpensive. Paper microfluidics is one of the examples to do microfluidics with paper. It's a very broadly distributed material. And another interesting, I think, frontier is organ on chip. So we can build organs inside microfluidic device. And at the beginning, when people do that, I think they maybe didn't communicate well, or I don't know. There was this idea that it was for regenerative medicine. We will build organ to repair people. This is not so much the case. What is very interesting with organ on chip is that you can have a human model in your device and you can do experiment with it. So it means that now I am able to do experiment on a human brain, on a human lung, on a human gut, And it's just so great because you don't need animal, and second, you have something that is really like the human. And you can do experiment with it, and it's inside a micro channel, and you can do a lot of fundamental research with that, and you can do a lot of medical applications, because this can be, if it's from stem cells, the organ you will study can be derived from the skin cell of a patient. So you take a patient, you take just a piece of skin, very small amount of skin, you transform it into iPS cells, you transform it into, for example, neuron cells or lung cells or bone cells or whatever, so that in your device you have you built a lung that is the same as the one of the patient, you built a liver that is the same as the one of the patient, and then you can do experiment on it. So this is a reality. This is a reality more than regenerative medicine, which is more complicated. So that's quite interesting. And you have many things in physics, in chemistry, and so on and so forth. So that's microfluidics. So it's basically what you find in papers is like you can do a lot of things, microfluidics, and then you have great phenomena, and then you have papers reporting it, and then you can integrate many things in a device, and then you have what we call lab on a chip. Okay, you integrate many things. So great applications. So in reality, it can be like that. So this is your microfluidic device. You see it's quite small. The first thing I see, I took this picture many years ago on the internet, is that the device is quite small, but you see that the experiment is not so small. You see that you have the microfluidic device, and you have here tubings, pressure control, camera, bench, students, computer, screen, chair. I mean, you have something that is rather big. So it means that the device can be very small, but the portability that is claimed a lot, claim microfluidics, portable, blah, 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 that you have in all millions of paper. Wow, the device is portable, but to make it work, it's not so portable, right? So imagine you have a pen, but to use your pen, you need to have a tube connecting to a tank somewhere, and so it's like that. Okay, and another thing is that, in fact, many times, it doesn't work. So it doesn't work not because your device has a problem, because your device, you can really precisely make it, and fundamentally it's very well designed, but you have clogging, you have bubbles, you have leakage, you have all kinds of this problem, and these problems sometimes are really a difficulty to do the research. Because you have to manage it, and this is a problematic, because if you are a student working with microfluidics, you want to do science. You don't want to spend your time to do plumbing, for example. And during this time, you don't produce scientific results. So that's something seriously challenging. So, as far as I know, if one day you want to do microfluidics, it's a great tool. So my advice is do microfluidics only if you have no alternative. Okay, if there is no alternative, there is no point to go to microfluidics. If there is no alternative, you can really do great things with microfluidics. So that's really nice to explore many things in microfluidics, because you can deal picoliter volumes, polarization. You can really do things you cannot do otherwise. So that could be really great, but do only microfluidics if it's to do something that is really worth it, and it's really special, that's something you cannot do otherwise. And second, know that fabrication is totally controlled. Okay, there will be no problem of fabrication. You can imagine any device you want, And if you have difficulty to make it, you will find somebody to make it, no problem. Any materials, no problem. But the control of the fluid might be technically, not scientifically, but technically challenging. So just be ready for that. The portability, as I try to explain, is not always so straightforward. And also, if we think again about reconfigurability, usually when you have a device, it has a specific design, and it is just a dedicated purpose. So I was interested when I started to be in this adventure of microfluidics when it's beginning in the 2000s. It was the beginning of microfluidics. I was interested to see if we could imagine some new actuation principles. So using these two stimuli, lights and magnets, where we could manipulate these fluids. So I didn't go to devices. So I don't say that what we do can be really used for devices, maybe not. But it was the opportunity to study interesting phenomena. How can I use light or magnet to manipulate small amount of liquids? So for that, I would like to discuss with you how we could go from light to liquid motion. We'll show you some examples from literature, and then after I will show you some things that we have done. So if you want to use light from light to motion, you have to consider what kinds of motion you need some energy. So what kind of energy we can transport with light if we want to do something. So the first thing we can think is the fact that light, as you have photons, so these photons, they have momentum, okay? So if they arrive on the surface, they will hit the surface and they will apply a force, okay? They have momentum. So when the photons arrive on the liquid surface, they will hit the surface and they can deform it. So there was an amazing researcher, Ashkin. He's actually the person who invented optical tweezers. This guy was an amazing person. They gave him a Nobel Prize. He was already 95 years old, and it was a bit strange because this guy should have got his Nobel Prize much before. He was a very creative person, very kind person apparently, with very small lab, but he had done many things. He invented optical tweezers. He built the device for Stephen Chu, who got the Nobel Prize for optical cooling, for example. So he's an amazing guy. And he was the first person who tried to do this optofluidics, I think. And his idea was to say, okay, I take a laser and I push and pull on the surface. So I would like to have somebody who can you estimate the size of the deformation you can have if you shine light on a liquid surface? So what kind of deformation you can get? So you are not transparent, but maybe you can estimate that? Come. You can just estimate it. We'll do something very simple, nothing complicated. So okay. Well, we can do let's write with another color. It's okay. Okay, so you have this. Okay, we want to estimate this deformation. We have a force. So what kind of force? You know the range of force we can just because of the photons that are transported by a laser, the order of magnitude. In Newton, you have some idea? Yeah, in Newton, yes. The force typically that is transported by light is of the order of 10 piconewton. Okay? So what is the deformation? Roughly. So so the surface is flat, right? Why is it flat? What happens when I deform the interface? Yeah, so what is resisting to this deformation?
Force is not affecting the same.
Because here I suppose I have a laser, and it's a picture, but what resists to the deformation? No, in your fluid is static. In the fluid, what resists, you want to deform it, right? Surface tension, okay? So surface tension is what?
Water for this.
Yeah, we'll see, but I mean in terms of force and so on.
Force by length.
Okay, so the deformation will be typically yes. So the deformation will be typically the force, right, divided by the surface tension. Yes.
On the liquid, we have this value.
Yes. So
Per meter.
so yeah, water is like what? It's 70 millinewton per meter. So if you take 100, just to make it simple. Yes. Yeah, take 100 for the calculation, it will be easier. Here, 100. Yes. 100. Yeah, it's closer to 70. Ten minus 11. I don't know. So you have what? 10 piconewton, 10 minus 12, yes. So 10 minus 11 divided by? Right. Okay. Yeah. So it's quite small. You see, I think you made maybe there is a mistake in the order of magnitude, but you have like, oops. Ah, there is something. So you see that if you just look at it's okay. Huh? If you just look at the dimension level, if you just make simple, very simple scale estimation with a typical with a typical surface tension, the very large like water, it's 70. Water is very high cohesive liquid, so it has high surface tension. You have deformation that will be like 0.1 nanometer. This is what you have found. And if you go to 1 millinewton per meter, very low surface tension, you can expect something like 10 nanometer. So you see that you have something that is around nanometric deformation, which is much below the capillary waves you can have on the surface. So you see that it's very difficult to do that. So what you can do is you can take some very strange system that can have very ultra low surface tension, for example, something close to demixing or some very strange system. And in this case, you can get some deformation, but only if you go to very exotic system with very low surface tension. So that's interesting in the principle. It was done so many years ago, but you are very far from manipulation. So with this idea of optical coupling, you can use optical tweezers, and in this case, you can trap particles, but you can also use angular momentum to make things rotate. So there's people who did this, especially David Greer in the US. Okay, it's nice, you can make this guy rotate. You can, for example, trap this. So you have colloids here. They are trapped in an optical hologram, and then they make this as a snake. I think snakes are very respected in India, which is very important. So you make this like this, and you see that this guy is moving a little bit. So they move here, and this creates a small flow, and this flow will push a little bit this tracer. So it's possible to do things, but you see that it's not easy. First, you need optical trap setup. Maybe you need optical trap holograms if you want to manipulate many particles. You need to do fabrication. That is not so easy. So usually that is quite high-tech stuff, and it's not really for portable system. So that's, I think, one strategy. And this is maybe a bit more exotic, but just to be complete, some people were a bit brutal, but they just take this big laser that can deliver very high energy. So neodymium, this Nediaga laser. So they just put a lot of power in a very small space, in a very small spot. So this creates a cavitation bubble, and because of the cavitation bubble, you can create droplets. So this is also okay, but I found it very brutal force for generate just droplets. We can generate droplets with a micropipette. So to use an ND-YAG laser to do this is a little bit extreme somehow. And it's quite invasive method as well. You don't want to be here in the microchannel when the laser is turned on, right? So that's a bit powerful. So just there are things that can be done, but this will be more laboratory experiments and like for some physics. We can think also that light can have also thermal energy. And this is quite interesting, and also photochemical energy. And the idea is that maybe instead of targeting bulk force, we can target interfacial force, because in microfluidics, if you divide the surface by volume, you scale as 1 over the size. So when you decrease the size, the surface becomes more and more important compared to the volume. So interfaces are maybe a very nice target. They are very nice targets because, okay, they have surface tension, but they are soft and they are deformable. And we saw many examples. If a spider is capable to do that, maybe it's not that difficult, right? So, and you can create easily a lot of surface, for example, if you lower the surface tension. So surface tension, you know what it is. It is the energy you have to pay to create interface. And create interface means you can create a liquid, or you can deform an existing interface. So this is energy to pay. So it is the force to apply if you want to do a given deformation. So if I have a lens tense piece of bed sheet, my thing will be more deformed, and if it's more tense, it will be less deformed, right? And then if you just consider this idea of tension, you understand that if I have a gradient of tension, then this liquid will pull the liquid here. Okay, so you will have, if you pull more here, you will have a flow. And this flow is, as you know, most of you, is called a Marangoni flow. So when you have an interfacial gradient of, interfacial energy, then you need to have a flow. And this flow is called the Marangoni. And it's quite interesting to see that if you just look at how the speed of this Marangoni flow scale with the surface tension, the main source of this dissipation is the viscosity. And if you just take usual liquid, you see that the gradient of 1 millinewton per meter is enough to reach 1 meter per second speed. So you see that if you look at static effects, it's not so easy to deform an interface. You need to put surfactant and so on. You can write the Laplace equation. You see that you need a pressure to create curvature. But what is very nice with gradient is that you can have very nice dynamic effects at the interface. Now, just for you to remember, we have a tendency when we speak about Marangoni, so we always say it's from low surface tension to high surface tension, okay? So we have this idea that everything is coming from infinity and do like that and go far from infinity, like if the Earth was flat, right? So I hope we agree here that the Earth is not flat. So usually the liquid is not infinite, is in a container. So when you have a finite liquid, of course, you need to have recirculation. Okay, so always never forget that when you have a Marangoni flow, yes, it's directional, but it's locally directional. There is always recirculation. So this Marangoni effect you can see in nature. I mentioned this insect that releases surfactant, create Marangoni flow and is propelled. You can do it, this very simple experiment of soap boat, a piece of soap. It releases surfactant at the back and then you can propel your boat. You can use camphor because it evaporates so that your surfactant go out of the surface and so on and so forth. And you have the famous examples of the tears of wine, where you take any alcohol you want. You just need to have a mixture of water and alcohol. Actually, you make a film, and if you just wait a bit, after a while, you will see an accumulation of liquid at the top of this film. And then a bit after, you will see these beautiful tears. And in fact, what is important in this phenomena is not the tears, but is this part. Okay, you will see that you have accumulation of liquid at the top of the film. So it means that there is liquid climbing up, and this liquid is climbing up because you have evaporation that is stronger where the film is thinner. So you enrich the system with water, surface tension is higher, so here you pull the liquid and you have this Marangoni. This tears of wine is another instability, so it's just a manifestation of the accumulation of the liquid, but the Marangoni is not the tears, but it's the fact that the liquid is going up. So interfacial gradients can induce significant flows, and also weighting is quite interesting because you don't need so much things to have this big difference of weighting. So you know that if you consider a theoretical equilibrium where you just have interfacial energy, if I take a droplet on a surface, I just look at the contact line, and if there is no other force, it's only controlled by the difference in interfacial energy between the solid and the gas, the liquid and the gas, and the solid and the liquid. Okay, and this simple force balance gives you that the cosinus theta is the difference between these two interfacial energy and divided by the liquid gas interfacial energy. So this is very simple. It's quite interesting, and to keep in mind that in the contact angle, you have three interfaces, okay? Always, this is something we tend to forget. We speak many times about, oh, I have a hydrophobic material or blah, 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 blah. No, please speak about contact angle, okay? Because if you speak about hydrophobic material, you consider only this interface, solid liquid. Okay, but your contact angle, you see that the solid liquid is here, but the solid gas is very important. Okay, and the material is here and is here. So this is what you can call it hydrophobic, hydrophilic, how materials likes or not water. But don't forget that there is air or gas or whatever. And this component is as important as this one, plus of course the surface tension of the liquid. So this is nice to always remember that in a wetting, you have 3 interfaces to consider, and never forget the solid gas interface. The thing is that, of course, in this representation, it's not so, you don't have to remember this equation because it's very easy to find. And also you can find on internet or whatever. But what you need to remember is that in this cos theta that we write by the Young equation or whatever, there is no other forces than interfacial energy. This is what you need to remember. As soon as you will have additional forces, there will be something else. You cannot just use this equation as long as you have other forces. It looks very simple what I say. I can tell you there is a couple of papers by a famous group published in Ungoverned Chemistry and other journals, but there is at least there is famous. They are doing a surface tension measurement, and they claim, so they had a solution with a surfactant and some iron salt inside. And they claim to have a magneto-sensitive surfactant, which is great. I would love to have magnetic sensitive surfactant, right? I tried to do it and I failed, but was something I was really wanted to make is magneto-sensitive surfactant. Surfactant that could change with you put magnetic field and you change surface tension. That could be really great. So they claim that, and they do pen and drop experiment. So you have done, some of you, pen and drop experiment, okay? So they do the pen and drop experiment, and they take a magnet, put it below the drop, and the drop was deformed because the magnet makes a force on the liquid that is containing iron salt. And then the machine, which is a very kind machine, very serious machine, the machine fits the shape of the drop with the Laplace equation. And for the machine, there is Laplace equation versus gravity. So the machine sees the drops that deform, so it says the surface tension decrease because it fits the Laplace equation. But you cannot do that because you have a magnet. You have an additional force. So you cannot say that your droplet is just following the Laplace equation under gravity. There is an additional force, but the machine doesn't know there is a magnet. So the machine says surface tension decrease because the droplets changes shape. And then these people say, oh, we have a magneto-sensitive surfactant. It's amazing, great, and go on to chemistry and so on. So to say that sometimes it's just good to just think about what is going on. That's quite important. If I take my droplet and I go on zero gravity, my droplet will be spherical. But surface tension is not increasing, right? So just remember that here there is nothing else. So as soon as you have additional forces, then you can have different consideration when you look at your contact angle and the wetting properties. The thing is that in reality you have other forces because you have many things that can act on the contact line that the force can be. So if I take a solid and if I make many drops on it, if I measure the angle, what I will find is I will find many values of this angle. And it's quite interesting that if I do the experiments, if I do many experiments, I will find that I have a lot of values, but they are always in a specific range with a maximum value that is what is called the advancing contact angle and a minimal value that is the receding contact angle. And these values are interesting because you can measure, and these values represent what is your system, what is your wetting situation of a liquid on the surface. And then if you want to advance a meniscus, you need to reach this angle, and then the meniscus will advance at a constant angle. And if you want to withdraw a meniscus, you have to be below this angle. It's very simple, but it can explain a lot of things. A lot of things in drying, drop drying, and so on and so forth. And now, what is interesting is to consider a situation where you have a gradient of contact angle in a droplet. And now if you have a gradient, you see that here, my Laplace pressure is higher than here. So then I should have a flow in this direction. And this guy will move only if this can beat this hysteresis of contact angle. So typically, you will have motion if your gradient of a contact angle is larger than the hysteresis. So with that, you understand that you can use confinement gradients to create transport. So if you have a conical fiber, as I mentioned in my first talk, then if you're in a wetting situation, the droplet will go toward the larger diameter. And if you are in a confined situation, if you have gradient confinement, the droplet will go towards the lower diameter until you reach the static point defined by the hysteresis of contact angle. So this is used in nature, as I show you, spider webs where water is transported along the increasing diameter and will stop at some position, and by these birds that can use this gradient of confinement to make liquid move in the beak, and actually is oscillating to make a ratchet so that it can make it jump the different static point. So we have the dynamic capillary effect, and now we can use these principles to use light. And one of the way to use light is to convert light into surface tension through the change of temperature. So for most of liquids, because when you increase temperature, you decrease the cohesion, so you will decrease also the cohesion at the surface, so you will typically decrease surface tension, but you can have some situation where surface tension increase with temperature. For example, you take a polymer, and you have a part that is hydrophilic, a part that is hydrophobic. So surface tension is, for example, it gives some surface tension. So this polymer surfactant is at surface. We can understand that if I increase temperature, maybe I can make the hydrophobic part more soluble. So maybe the surfactant will go to the water phase, and then the surface tension can increase. So in the presence of some surfactant, you can increase surface tension. So it means that if I just put a laser on this droplet, if my surface tension decreases, I will have a Marangoni stress. So the question is, where is my droplet going? If it moves, where is it going? Let's vote. Let's vote. Who says going to that direction? One, two people. Who says it's going? Three. Okay. Who says going to that direction? The same person. It's great. So, no, so you are for this direction? Okay. It's an easy choice. So this tonight we go to the beach. So you know how to swim? What? Okay. Yes. It goes to this direction because you have a stress like that, so the droplet can go to the direction. This is symmetric. You can cut into two. You imagine it's a bicycle. When your wheel is rotating like that, you go to that direction. Okay, so the droplet will be pushed here. So it will be attracted by laser. So it's funny, it's like an optical tweezer, but you use capillary force and you can trap objects that are much bigger, like a droplet. And you don't need big laser to do that. And of course, if you take the other situation where you have d gamma over dt that is positive, you will be the opposite, you will push the droplet. So if you have some kind of strange surfactant, for instance. And this is the first paper, to my knowledge, where people use this principle. A very beautiful paper, very simple but very nice. They put a laser on one side and they could push the droplet like that and they could combine. So it means that they were probably in a situation with a d gamma over dt that was positive. That was not like simple thermocapillary effect. And then there was this French group of Charles Barroux. They did a lot of macrofluidics application with that. So for example, they block some meniscus using a laser. They control the fusion of droplets like that, and they do some kind of valve experiment. So you can start to do something. Maybe the small problem I see is that you need to heat the sample, so you have to be careful that you should work with simple compatible. And in this experiment, you need some laser power, unless you use this very smart way that they are doing in the lab of Subramanian Varnakotu, where if you use photonic effect, that's cool because then you don't need a lot of power to create temperature. And in this case, you can do very nice thermocapillary effect without spending so much energy in the system. So another way, which could be more on the chemical coupling side, you can use photosensitive substrate. And in this case, this is the first example by Whitesides again, where they prepare a surface with a gradient, and you see that the droplet is climbing the surface. It's very old work, but it was the first time I think people could watch a droplet climbing. And we had this idea to make this in a bit simpler and funny way, to say maybe instead of making a gradient on the surface, we can take a droplet so that the droplet will create its own gradient. Okay, and to make this gradient, we didn't want to do complex chemicals. We didn't want to do organic solvent because this was people were used doing. We just take water, just take surfactant, and in this surfactant they are cationic, so they can adsorb on glass. And if you imagine that your droplet is moving, then you see that you have a gradient because you have adsorption of surfactant, and this place has shorter contact time than the rear of the drop because the drop is moving like that. So you have more surfactant. Okay, so if the droplet is moving, you have a gradient. And if you have a gradient, the droplet is moving. You know, it's like if I take, for example, what can I take? Hot ghee in a pan. And I take this hot ghee and I put on my foot, and then I will escape because it's hot. And then, of course, I'm carrying the hot ghee, so the hot ghee is still on my foot, and I go on and go forth, and then I'm always moving. This is what this droplet is doing. It's putting hydrophobic things, so then it wants to escape, and then it can self-propel. So it's a very simple system, CTIB, water, glass, and you have this very nice self-propulsion. And you see that with this very system, there is nothing special, no chemical special, no organic solvent, and the droplet can climb vertically. And you can just take a pen and you draw a device, and the droplet can move in your device. And then if you want to use light, you can use photosensitive substrate. And this is the first example where people take a solid substrate with photochrome, here it's pyropiran, and then by applying gradient of light, they create a gradient at the level of the droplet. And the droplet is moving a bit, but it's difficult, as it has been already explained, that moving on a solid substrate is not something easy. There is something I find quite interesting in terms of concept, at least, is this idea of optoelectrowetting. In electrowetting, it was discovered by Lippmann in the 19th century, and it took 150 years that people reconsider this as an interesting behavior. Like if you take a water droplet on an electrode and you put an insulator here, if you apply an electric field, you will make a condensator, a capacitance, meaning that you will create charges, and these charges will change the wettability, and the droplet will wet. So this is used for liquid lenses, for instance. It's used in drones. It's used in some smartphone. So now, if you in this electrowetting, you don't use a uniform electrode, but a pattern electrode. And if you apply, for example, the electric field only on this side, then I create my gradient. And this is, if it's larger than hysteresis, my drop will move. Okay, so then you can do this electrowetting device where you can manipulate drop. But you see that it's a bit tricky because you need to control the electrical voltage you apply at the level of single drop. And you may need to make a gradient. So this is a little bit challenging in terms of device. And there was these people who were a bit forgotten, I think, from the group of TU in California, already in 2003, a time where microfluidics was really at the birth, but they had this idea that maybe instead of printing electrode, I can make images. Okay, so this idea is that they put a photoconductor and this insulation layer, and meaning that you will have this this voltage apply only where you have light. I know it becomes so easy to make gradients because then you can just send an image to your device, so you have a uniform electrode, but then you put an image, and then it's like you have a virtual array of electrode, and as soon as I change my image, this array of electrode is changing, and then with that you can manipulate droplet as much as you want. Very interesting concept to my point of view. And then confinement, I show you the bird, I show you the spider, so you know that you can control fluids by confinement, gradient of confinement. And then people had the idea that you can use the gradient of confinement to control it with light. I was actually a reviewer of this paper. And you will see it's quite interesting. They do like the bird, but using light. So yes, they have a polymer, and this polymer, depending on the light, will change the diameter, and depending on light, they change the diameter, and with that they can control the liquid motion. So we have all these aspects that you can use to use light to do a fluidic operation, and I would like just to show a few examples where how you can directly address capillary effect with light. And this idea to me it was the most straightforward because in life, when you want to change surface tension, you don't use laser, you don't use temperature, you don't use pyropiran, you don't use complex stuff, you use surfactant, right? So we had this idea to just make photosensitive surfactant, very simple molecule, and you can change surface tension. it doesn't change that much. It's not very optimized molecule. We didn't try to do some complicated chemistry. It's a very simple molecule. The surface tension changed by a few millinewton per meter, but we can make gradient, and as soon as you can make gradients, you can make a motion. So we describe this first concept of chromocapillary effect, where the wavelength makes a gradient. So we just put a difference of light, UV and blue. UV has a higher surface tension, so you have a higher surface tension here, lower surface tension here. So like the swimming I showed yesterday, if you have your gradient toward the high surface tension, then you have to go to this direction, okay? So it's like this, like my swimming is like that. So this is the first experiment. My droplet is here, I put light, you see it's pushed. And if I revert the gradient of, if I revert the wavelengths, if now I put blue light, my droplet is attracted, and then I can pull on the droplet. You see, you can go on the other side, and now I can make a trap. If I put blue lights that attract the drop in the middle and UV around that push the drop, then I can make a trap, and we can move a single drop, and you see how useful it is, because we can send this kind of messages to the whole world. But the small problem with this is that here you need to make a gradient at the level of your droplet. So it means that either you deal with big droplets, either you are very good in optics and you make something very precise, which is not my case. So I wanted to find something a little bit simpler. Actually, we can, something much simpler is just to look at the water-air interface. And here, if you just put light, you have a mahogany flow toward the light, and anything on the surface will be transported. So it's a very simple experiment. You put light, and you see that the droplets are attracted a little bit like insects, that when they see light, they want to go toward light. And here, any drops will go to the center, and I can program their fusion. And I think in this time, already 10 years ago, but we did the first organic reactions controlled by light like that, because we combine some drops having different organic compounds. But this is oil droplets on water, and I tend to prefer water than oil in general. So I wanted to know, how can I transport water on water? And I think you have the answer, right? How can I make a water droplet on water? Right? What? Liquid marbles, right? You have done in hands-on experiments. So we had this idea that maybe we can take a liquid marble. At that time, when we did the experiment, I don't think, at that time, I didn't see any liquid marbles on water, on liquid. Everyone were putting liquid marble on solid. And we say, okay, let's put on liquid. We had a bit of challenge. You had also some challenge, but finally, we did the experiment. So this is some powder by Nikita. He was a bachelor student doing an internship in my group at that time. He's using an optical table because he's a kind of physicist guy to do that. But you make the marble, as you know, and we put on the surface. You do this, and then you transfer this little guy like here. And this is my little liquid marble. You see, it's very dirty, okay. We were super happy. So for you, it's very normal, because for you, it's very normal. That time, we were so happy to have a liquid marble floating on the surface. And then we did the experiment. So the experiment is like that. I have my liquid. I have my liquid marble here, okay? And I have an LED with UV light like that, okay? So my light is going to this direction, okay? So now I will turn it on. And usually, the audience say, wow. Okay. You are very honest. So you see that we put light and we are so happy, we make a mahogany flow, it moves, and you see it's transported mahogany. So we repeat the experiment, same experiment, just we put less liquid in the stuff. Okay, so same experiment, just I have much less liquid in my petri dish. Okay, but it should be, whoa, because you see it goes in the opposite direction. It's a bit surprising, right? So we could say, maybe the mahogany is opposite for some reason. But if you look at dust here, I don't know if you see the dust. Do you see the dust? I don't know if from your arm, but here we can see the dust. The dust is going to the light. So the mahogany flow is toward the light. So our marble is moving oppositely to the flow. So here we have anti-mahogany motion, okay? So I don't have much time, but to explain this, but in fact, we could explain that it's because when you confine liquid, the mahogany stress will create deformation of your liquid. So when we tend to forget because usually we are in a system where the liquid is so thick that when you create a mahogany flow, you have no constraint. So everything, you can have this vertical flow and then recirculation. But when you confine, you have a stress that can be converted into static deformation. So we can measure the thickness, and you have this transition behavior. When you are at low thickness, you go against the flow, and the more you are small, the higher you go, and where you are at high thickness, you go with the mahogany, and when you increase the thickness. So we can measure the deformation. So when you have a thick liquid, it remains basically flat, and when it's confined, you form this bump. This is time interval 0, and this is how it goes with time, and it's stabilized, and it makes this kind of bump. And because we have a bump, if the liquid marble is not heat, it can just slide like on a slide. So we can just make a very simple static model. You can estimate the variation of the height, which is just the gradient of surface tension divided by the thickness, which is normal. And you see that the higher the gradient, the higher you can have an increase of your height. And then you can just make a simple model where you just consider that the marble can be transported by the liquid surface flow, by the mahogany flow, and can also be transported by gravity because you have a slope. And you end up with this quite interesting equation. Like when you are at high thickness, you just have a simple mahogany effect. So basically the speed is the delta gamma divided by the viscosity. So basically the speed is the speed of the mahogany at the interface, more or less. But what is interesting is that when this thickness becomes very small, then you see that this becomes predominant. So you change the direction, and now you have a speed that increases when you increase the confinement. So it's something like that. You can model the flow. So when you are high thickness, you have recirculation. The marble follows the flow. And when you confine, you deform the liquid. And now your marble is going to the opposite direction. So it's quite interesting that you have a system that is controlled by gravity when you are below the capillary length. It's not something very usual, but it's when we are below the capillary length that our system is controlled by gravity. So we call it the slide effect because the guy is going sliding on this deformation. So you could say I'm not very honest because I didn't speak much about microfluidics, but I told you that in microfluidics, when you do droplets, it's very important to consider the solid, and that is controlled by the wetting. So our idea was if you want to control microfluidics, this is what we need to target. Okay, So this is what we did in macrofluidics, which we control the weighting, and basically by adding a photosensitive surfactant, we can switch between the two behavior. And when you put this in a microfluidic channel, your system is blocked. And then when you put light, you generate a stress, and you can release a single drop each time you shine your light. You see, when I shine light, I release a laser, spicoliter. And when you have a continuous flow, I can play on this weighting, deweighting, and everything is fixed. When I apply UV, I have deweighting, I create droplets, and then when you remove UV, I have a continuous flow regime. So you have like that a way to cut light using lights. It's a very old experiment, but I think it was very new at that time. And we use it to do mixing. So the experiment is very simple. We just take two oil phases that are different. We want to mix, we put water in between. So when it's continuous, the two compartments are separated. And then when we put light, we will create the droplets. These two compartments will be in contact, but we are at high Peclet number. It means that they will not mix easily, but our droplets, they can move and they can work as a stirrer. So we can mix the liquid like that. So you see when you apply UV, there's two liquids. Here it's fluorescent, here it's not fluorescent. When you apply UV and make droplets, the two liquids are fluorescent, are mixed, and when you remove UV, they are separated again. So you can continuously mix and go back to a separated system by the system. So it's probably the first optofluidic mixer that was described in literature already 12 years ago. So you have all these kind of things, and I would like to, I think what you need to remember in all these examples is not what we did, not what other people have done, because everyone is happy with controlling something, but it's more what happens. And what happens, I think, is the fact that small gradients of interfacial energy are really powerful to create interesting behavior of the fluids. And then you can find different ways to generate these gradients, but in general, this can really lead to very rich phenomena. And I think interesting scientifically and potentially useful as well. And just already late, but I promise magnets, so I'll just show you one example of what we can do magnet. A magnet is nice because we are not transparent, as I said at the beginning, and also it's probably something that is very compatible with the application. So we wanted to move objects using magnets, and we didn't want, of course, to use magnetic particles because this is something already well established. If I have a liquid marble with magnetic particles, I can trap my liquid marbles. So we wanted something more fluidic. So what we did, we take a water solution with some salt inside, so it's water phase. Here I have a liquid marble, and here is where I have my magnet. And you see when I approach my magnet, my liquid marble is pushed away. And it's pushed away because I will do this deformation just like in this slide effect I showed before. So I deform the liquid, and I use the liquid deformation to move this liquid marble. And what is quite interesting is that you can play a bit because water is diamagnetic, okay? So if I approach a magnet to water, it will be repelled, okay? But then I can play because I can adjust the permeativity of my system. So if I put at 0, so I have no deformation, and then if I put water, this droplet, this marble will be pushed a little bit by the magnet, but just very small deformation. And I can do the opposite. I can put the susceptibility at 0 in my marble, so it means that my magnet will not put any force on the marble and will just deform the liquid. And you see that here I have significant speed. And if I combine both deformation and the diamagnetic effect on the marble, I have this final size. And if you do model, or if you see the experiment, you see that most of the component of the transport is a deformation of the liquid, not so much the force on your object. So then you have a universal way to transport things, and you can, for example, manipulate liquids. So these are just simple oils. There is no particle magnetic whatsoever, and you see that with a magnet, I can manipulate this liquid droplets in a way I want. So with that, yeah, I show you how light fluids, light-driven microfluidics, optofluidics can be other things. I don't have time, so I will stop here. And thank you for your attention.
Thank you, Professor, for the wonderful talk. So shall we take the questions now, or?
If there is one question, and otherwise we can discuss during the hands-on session as well.